Chapter 1.11.10 API Priority and Fairness. Summary. In Kubernetes version 1.29, the API Priority and Fairness (APF) feature helps manage the Kubernetes API server's load during high traffic. APF classifies requests, uses queuing to manage bursts, and employs fair queuing to prevent monopolization by any single source. APF utilizes flow schemas to categorize requests and allocates them into distinct priority levels. This prevents any request flow or priority level from starving others, ensuring fair resource allocation even at high concurrency levels. Administrators can tweak APF settings to optimize resource usage by adjusting parameters like concurrency shares and priority levels. Some requests are exempt from APF control, ensuring vital operations always proceed. API Priority and Fairness. The Kubernetes version 1.29 API server has new controls to manage overload situations. Maximum requests accepted are limited by certain flags to prevent crashes due to excess traffic, but these are not fully effective. The API Priority and Fairness (APF) feature offers enhanced request management by classifying and handling requests more precisely, reducing rejection during sudden traffic surges. APF uses fair queuing to dispatch requests so no client is unfairly deprived of API server access, even if some have higher priority. While APF works well with standard controllers that react adaptively to API failures, it doesn't apply to all long-running requests like remote command executions. Watch requests do fall under APF checks but are exempt from maximum in-flight limits if APF is disabled. Disabling API Priority and Fairness. This code snippet is disabling the API Priority and Fairness feature by setting the runtime configuration for flow control to false for the Kube API-server. The API Priority and Fairness (APF) feature is enabled by default via the Enable Priority and Fairness command line flag. It utilizes the API group with a stable v1 version and a v1 beta 3 version, which can be disabled. To disable the APF feature, use the command line flag. Enable Priority and Fairness equals false. The feature includes a stable v1 introduced in version 1.29, with a deprecated v1 beta 3 version. APF involves a stable v1 and a deprecated v1 beta 3 version. Disabling requires specific command line flags in Kube API-server. Recursive server scenarios. In recursive server scenarios, priority and fairness in handling requests must be approached carefully. An example is when server A, while processing a request, sends a subsidiary request to another server B. Priority and fairness control can affect both the initial and subsidiary requests, potentially causing priority inversions and deadlocks. This occurs when requests are classified into different priority levels but handled unsupportively. Recursion examples include the Kubernetes API server calling server B through an admission webhook and then receiving a subsequent callback. Another example is delegation requests to server B through an API service object. To avoid issues, it might help to assign a known priority level to the original request and classify the subsidiary requests to higher levels, making them exempt from control limitations. If the original request can have any priority, it may be necessary to exempt controlled requests from limitation or disable priority and fairness on server B altogether. For non-Kubernetes servers, disable it in the code. Concepts. API Priority and Fairness Overview. API Priority and Fairness, APF, helps manage incoming requests to an API server by sorting them into priority levels and assigning requests to flows. This system prevents busy queues from being overwhelmed while ensuring equal request processing opportunities, even when the server is under load. The feature includes several subcomponents, such as flow schemas and priority levels, both critical for efficient API operations. Managing priority levels. APF introduces concurrency limits based on priority levels. Without APF, server capacity is controlled primarily by flags that limit ongoing requests. However, with APF, requests are distributed among designated priority levels, each with its own limit. This ensures that no single priority level can monopolize resources, thereby allowing critical tasks like leader elections and built-in controllers to operate smoothly, even during a traffic flood. Concurrency and seats. In APF's concurrency management, each request occupies a seat. Most requests take only one seat, but some, particularly list requests, may occupy multiple due to their load on the server. This seating notion ensures that hefty requests do not overburden the server, enabling more balanced task distribution and smoother operations within priority levels. Execution time and queuing. Watch requests, essential to APF's operations, hold seats until their initial processing is complete. Once the initial burst of notifications is over, they release those seats. Requests are queued using a fair queuing algorithm that ensures equitability among different request flows. This prevents a single client from overwhelming the server and facilitates load redistribution. Flow classification and shuffle sharding. When requests reach the server, they are sorted into flows based on criteria like user or resource namespace. These flows consist of queues processed equitably, avoiding the dominance of high-intensity networks. Shuffle sharding is a method that allocates request processing power effectively, ensuring fair distribution without overloading specific queues. Handling exempt requests. Some requests are considered critical and are exempted from the limitations imposed by APF. This safeguard ensures that necessary operations continue undeterred despite flawed APF configurations that might otherwise stymie essential processes in the API server. The exemption allows the server to prioritize tasks of utmost importance without constraint. Resources. Part 1. Overview of Flow Control API resources. Flow control in an API involves two key resources: priority level configurations and flow schemas. Priority level configurations define priority levels roles, their share of resource allocation, and control over queuing behavior. On the other hand, flow schemas are designed to classify incoming requests, routing each to a corresponding priority level configuration. Part 2. Priority level configuration details. Every priority level configuration specifies a standalone limit for active and queued requests. It uses nominal concurrency shares to determine resource distribution, allowing system administrators to adjust server traffic by tweaking the max requests in-flight setting. Changes see concurrency limits swell or shrink uniformly across configurations. Older system versions did not feature periodic adjustments, always applying the assured or nominal limits to the system. Part 3. Concurrency management in priority levels. Concurrency limits for priority levels feature upper and lower boundaries, determined by a percentage of the nominal limit. Adjustments occur based on recent demand, lending, and borrowing seats, ensuring fair responsiveness within set bounds. When priority and fairness are active, separate management for mutating and non-mutating requests is suggested by creating distinct flow schemas for each. Part 4. Handling excess requests. Reject or queue options. If requests exceed configured concurrency levels, the priority level configurations type dictates handling. For instance, the reject type discards surplus traffic instantly, issuing an HTTP 429 error. In contrast, queue type defers requests beyond the threshold, using shuffle sharding and fair queuing for balanced request flow management. Configuration can tweak queuing algorithms, affecting latency, memory use, or burst sustainability. Part 5. Flow schemas' role in request assignment. Flow schemas align requests to priority levels by matching predefined rules. Requests undergo a cascade sequence, adhering strictly to matching precedence. A single successful match assigns a request to an appropriate level, though multiple matches may lead to precedence conflicts. Flows can be differentiated by user, namespace, or not at all, ensuring balanced capacity distribution based on organizational needs. Part 6. Dependency and configuration considerations. A rule within a flow schema requires at least one matching subject and relevant resource or non-resource rules. Wildcards enhance flexibility, removing explicit matches. Careful distinguisher method choices prevent capacity starvation, aligning request flows to user or namespace needs based on system objectives. This enhances the control over whether all requests are considered a single flow or distributed differently. Defaults. The Kube AppServer maintains two main types of configuration objects: mandatory and suggested. Mandatory configurations enforce essential flow control that is inherent to the server's operation. Four key mandatory configuration objects include an exempt priority level for unrestricted requests, and a catch-all level ensuring all requests receive classification. Mandatory configurations address servers' built-in guardrail behavior. Notably, the exempt priority level bypasses any flow control, classifying certain system requests, like those from system masters group, as exempt. The catch-all level serves as a failsafe, ensuring all requests are classified, albeit with minimal concurrency shares. Suggested configuration objects offer a default system for managing cluster loads. The suggested flow schemas organize requests into 6 distinct priority levels based on their origin and nature, such as node health updates, leader election requests, workload types, and global defaults for general user commands. Each Kube AppServer autonomously manages both mandatory and suggested objects. Initial and continuous maintenance ensures that mandatory objects remain consistent with server standards and suggested objects remain customizable. Maintenance happens periodically every minute, which could lead to thrashing if different server versions coexist. Maintenance involves ensuring that mandatory configuration objects exist with correct specifications. Suggested configurations can have overridden specs, although deletions are automatically restored. New versions could trigger automatic adjustments, though users can control configurations by setting specific annotations. Maintaining configuration objects includes proper annotations reflecting control ownership. Any non-mandatory or non-suggested objects with the annotation apf.kubernetes.io/autoupdate-spec equals true single quote are deleted. Users can control suggested configurations by setting the annotation to false to prevent automatic updates. Health check concurrency exemption. The YAML code provided defines a flow schema named health for strangers with a matching precedence of 1000 and a rule that exempts requests to healths, lives, and readies paths with any verb from the system. An authenticated group, assigning them to the exempt priority level with the purpose of allowing unrestricted access for health check requests from unauthenticated users. The configuration doesn't give special treatment to kubelet health checks, which use secured ports without credentials. These requests are assigned global default flow schema and priority, risking overcrowding. Adding a flow schema can exempt these requests from rate limiting, but it allows potential misuse by hostile parties to send unlimited health check requests. To mitigate risks, using external security like web traffic filters can block outside cluster health requests. Observability. API Priority and Fairness Metrics Overview ***. In versions before Kubernetes version 1.20, label names for key metrics were inconsistent. Enabling the API Priority and Fairness feature in Kubernetes allows the Kube AppServer to export metrics that can help in monitoring system health and traffic handling. This ensures no critical traffic is unduly throttled and identifies problematic workloads. Key metrics **. The essential metrics provide data on rejected requests due to reasons like queuing issues, concurrency limitations, and timeout. Other metrics showcase the number of executing or queued requests, providing insights into operational bottlenecks. Gauge and histogram metrics **. Gauge vectors are used to track instantaneous numbers of queued, executing requests, and occupied seats. Histogram vectors are used for the duration requests spend in queues and analyze if configurations properly manage traffic, considering priority levels and flow schemas collectively. Concurrency limits **. Metrics provide insight into concurrency limits at various levels, indicating the nominal, lower, and upper concurrency limits. They also offer a demand and utilization perspective to ensure efficient workload distribution while avoiding overwhelming the server. Request demand analysis **. Through different vectors, the demand for seats is tracked, offering metrics on both historical and current demands. These help in understanding if demand exceeds server capacity, thereby triggering adjustments in concurrency configurations. Extended metrics for stability **. Additional metrics assist in recognizing events where requests could not be dispatched due to concurrency issues, measuring execution times, and analyzing priority level progress. This information allows fine-tuning the system to enhance stability and performance. Good practices for using API priority and fairness. This YAML configuration sets up a flow schema named List Events Default Service Account that matches requests for listing events resources in the default namespace with the list verb. It assigns these requests to the catch-all priority level and distinguishes them by the requesting service account in the default namespace. ###1. Understanding request handling and concurrency limits in APF. * Request overload and errors *. When a priority level's concurrency exceeds its limit, requests may face delays or get dropped, triggering an HTTP 429 error. Avoiding side effects *. Adjust the workload or APF settings to ensure availability of sufficient seats necessary for handling requests. Metrics for diagnosis *. Track specific metrics like rejected request totals, in-queue request numbers, request wait durations, and seat utilization to identify if APF is causing rejections. ###2. Strategies for workload optimization. Rate reduction *. Lower the rate of request execution to decrease seat requirements. Concurrent request management *. Limit large, costly requests to reduce occupied seats and latency. Optimizing list requests *. Utilize pagination to reduce seats or use watch requests, which require fewer concurrency resources. ###3. Recognizing effects of increased request load or latency. Request induction *. APF issues arise from increased load or latency. Long-duration requests may trigger more rejections. Performance indicators *. Unchanged workloads with rising rejections could indicate other control plane issues. ###4. Fine-tuning APF configuration for better performance. Config adjustments *. Modify flow schema and priority level configuration to accommodate workloads effectively. Increase seat allocations where needed. Resource allocation *. Balance and allocate seats for high priority versus non-essential requests, maximizing concurrency management. ###5. Tailoring priority levels and concurrency control. Increasing seats *. Utilize available configuration flags or horizontal scaling to uplift seat availability and manage concurrency effectively. Custom flow schemas *. Create new flow schemas or change existing ones to accommodate priority needs. Nominal concurrency shares and lending *. Adjust these to provide high priority requests a larger pool of seats. ###6. Isolating non-essential requests. Request segregation *. Isolate costly or non-essential requests via specific configurations, preventing them from affecting other flows. Flow schema configuration *. Map particular requests to low-seat flow schemas. Example provided for isolating list event requests.